Hello, this is Jim Holland. Greetings from North Carolina State University. This lecture is an example of one of the lectures I present in our course, Crop Science 746. It's called Plant Breeding Methods. And this particular lecture is an example of QTL mapping using several different methods with a real data set. The data set we are going to analyze in the example is a rice yield evaluation that comes to us from my friends at International Rice Research Institute, Gary Atlin and colleagues when they were there. They provided these data. The mapping population is a set of 130 doubled haploids derived from a cross between two diverse inbred rice line parents. The phenotype data we are analyzing is based on an experiment that was a randomized complete block design in 3 replications in a single year, in this case the year 2000. The initial phenotype analysis was already done. We are not going to discuss that portion of the analysis, but the initial analysis has been completed and the entry means, in other words the doubled haploid line means have been estimated, and the entry mean basis heritability was estimated to be 84% within this particular environment. And I will leave it for you to think about why it matters what the entry mean heritability is for a QTL mapping study. Does it matter if the heritability is 50% or 90%? And why does it matter? I'll leave that as a question for you to think about. We will consider it for the purposes of this demonstration that a heritability of 84% suggests that we have reasonably good estimates of the genetic values in this particular environment. The analysis will be based on a dense linkage map of markers that we will show on the next slide. Here is the genetic map of this rice population. Does not show all of the chromosomes, but it just gives you an example of chromosomes 1 through 8. The density of the molecular markers. In this case, the numbers on the left-hand side of each linkage group indicate the centimorgan position within the group, and the names of the markers are on the right. What does a data set look like for conducting QTL analysis? And what I have shown here is an example of an input dataset file that can be analyzed by the program QTL cartographer. So this is just an example of the beginning of what the dataset looks like, and the data file will have an extension of .mcd. QTL cartographer will recognize that and read it in as an input file. QTL cartographer is freely available, and you can Google it and find the website. It's from NC State. Dr. Xiaobeng Zheng and his colleagues created this software. What you can see up here, what I've got bold at the top, is some basic information about the linkage map itself. So there's some information on how many chromosomes there are, what the map position units are, the mapping function, the maximum number of markers per linkage group, those sorts of things. And those can vary depending on what your input data set will look like. And then below that, we start giving it information on the map. So you see this position where it says chromosome, chrome 1, and this provides basically a text input information that shows what that linkage group looks like that was on the previous slide. So I've only taken a very small subset of the entire set of marker map positions, but it goes from chromosome 1 down to chromosome 12, and then you will have this little flag that says stop, that tells it that's the end of that map, and then the file will continue, and I show that here on the next slide. And the next part of the file shows the genetic marker score information. So it gives it the sample size. I told you there were 130 doubled haploids. There's actually genotype data on 154, but the phenotype data is restricted to a subset of 130. And anyway, that's okay. We will give it the map and the scores based on the 154. And for those lines where we did not have phenotype data, we will just give it a missing trait value. Traits, number of traits that can be analyzed, there are 4 different traits, and we'll show those at the bottom. Below this, you have a translation table where number 2 in the genotype scores indicates that the genotype is big A, if we consider that the homozygous for the allele coming from one of the parents. And the number 1 indicates it's a heterozygote, and the number 0 indicates it's homozygous for the other parental allele. Below that, we start the markers. This shows the marker scores for a particular locus in the order of the recombinant inbred lines. The order matters here because the phenotype data has to be in the same order. We stop the markers at the end of the map, and then we start the trait information. So we have here S00MGY, that's the trait we're studying. And after that, these are the mean grain yield values for each recombinant line in that environment in the same order that we put the molecular marker scores. Now, the first thing we will do is demonstrate a so-called single marker analysis. And what this is a very simple regression model where Y, your phenotype score data, in this case, those will be the yields for each line, are modeled as a function of some overall mean, that's the B0, plus a regression of yield on the allele state at a particular marker. So we have B1X. So what we will do is we will look at the first marker in our data set, and we have it scored from 0, 1, or 2, or in this case these are doubled haploids, so everything is 0 or 2. And we're going to simply run a regression of yield on the number of alleles from a particular parent at that locus. And then there's some residual from that model. So that model will tell you to what extent there is a relationship between allelic state at a particular marker and the phenotype. And then we will repeat this analysis for each marker, one at a time. Okay, so the output from this, as shown below, from QTL Cartographer, and we have a list of the chromosome, and here I have just the results from the markers on chromosome 1, and we start with markers coded in the order that we give them in the map, so that's marker 1, marker 2, all the way down. There's a bunch I'm not showing, and then we have marker 33 down to marker 40. Now the B0 is the intercept, and you can see that that doesn't change very much. It should not change very much. That intercept should more or less be the same. It changes a little bit because there are some missing data, missing genotype data, that varies among which lines are missing data for a particular marker, and that will cause your B sub 0, your intercept, to change. But most of them are somewhere around 27, 26, 28. The B1 is the regression. So going from 0 score to a 2 score, you would say that the difference between those two groups is twice this regression value, 2 times the B1 value. And you can see at our first marker, the difference is 2.788. And then we have some likelihood information. And then we have an F-test for that is the next column, 1.441. And the p-value, or the probability of that F value, given in the last column, in this case it's 0.232, indicates the probability that you would observe a regression coefficient of 2.788 or greater under the null hypothesis. In other words, if there were really no QTL there, you could have an estimate of a regression value of a QTL of 2.788 or more 23% of the time. So we would suggest that that does not give us strong evidence that the null hypothesis is wrong, and therefore we conclude there's really no evidence that there is a QTL linked to that marker. Now we repeat that test at the position of the second marker, and we observe a fairly similar result of B0, B1 B1 in this case is a little smaller, so the regression coefficient is a little bit smaller, and consequently the p-value is a little bit larger. There's even less evidence for a QTL at the second marker. Now we do this test for every marker, and we continue on until you see here on marker 33, that's where we see our first significant result in this data set. And the B1 value here is 5.579, and that suggests that the mean difference between the 0 and the 2 marker classes, or the 2 homozygous genotypic classes at this locus, is twice that B1 estimate. So it should be about 11 units. And in that case, the probability is 0.017. So that indicates getting a regression coefficient estimate of 5.579 or larger could happen only about 2% of the time under the null hypothesis. And thus we conclude it's likely that the null hypothesis is not correct, and we suggest that there's a QTL linked to that marker. Now we move to the next marker, that's 34. The intercept's about the same. The regression coefficient's a little bit bigger now at 6.7, and the p-value drops to 0.004. So we suspect that there is a QTL linked to marker 34, and so on and so forth. Now, if you look at this result, these last 7 markers, or last 8 markers at the distal end of chromosome 1, all of them are significant at least at the 0.05 probability level. The question is, how do you interpret that result? Do you think that indicates that we have 7 QTL here? 7 different genes, or 7 different gene regions all affecting rice yield? We'll look over here on the right-hand side, and this is just to remind us of what the map is in this region. And the distance between marker 33 and marker 44 is about 60 to 70 centimorgans, so it's a reasonably large area on the chromosome. The highest significance is found at chromosome 1, marker 39, and that has a p-value of 0.005. That marker we see is positioned at about 255 centimorgans on the map. Look at the regression coefficient there. It is actually negative. It is minus 7.4. Now that's different than what we saw in these markers that are more proximal, such as markers 33, 34, 35. Those were plus 6.7 or thereabouts. So the effect estimate has changed in sign. And the question for you is, what does it mean for the additive effect estimate to be negative instead of positive? And I won't answer that question unless you ask me. I'll let you think about what that means. So let's go back. What do you think? Do we have 7 different QTL here? Typically, the interpretation is not that we have evidence for 7 unique QTL down in this region, and the reason is very simple. The reason we identify some effect associated with marker 34 is not because the marker locus necessarily is the causal gene or the QTL. It's because that marker is linked to the QTL. And marker 34 is linked to the QTL, and marker 35 is very close to marker 34. So marker 35 is linked to the QTL as well. So this whole set of markers here in this region between, let's say, 33 and about 38 are probably all linked to the same QTL. That covers a region of about 25 centimorgans. And the effects are all positive, but they're largest sort of toward the middle of this region. Something different is going on at marker 39 and marker 40, though. The effect sign has changed, and those markers are a little bit distant from the other ones. There's kind of a gap between markers 38 and 39, and that's where you see the effect estimate changing from positive to negative. So I think we would conclude that it's likely that there is indeed at least one different QTL in the region around markers 39 and 40 compared to the QTL that we suspect is in the region around marker 35. So let's hypothetically imagine that we had a marker 39.5 that mapped. Let's assume that we had a marker 38.5 that was located exactly halfway between markers 38 and 39. What kind of result in terms of the regression coefficient for the QTL mapping phase would you might expect to find at such a marker? And again, I'll leave that question for you to think about. Now let's consider interval mapping. And as we discussed previously in the course, the way interval mapping works is that we consider the interval between two marker loci. So if we have a doubled haploid population, we have 4 possible 2 locus genotypes at the marker loci. So you can have a marker genotype where the line is homozygous for the parent 1 allele at both marker loci A and B, or it could be both homozygous for both A2 and B2 alleles at those 2 loci. Those would be parental classes, and that's at the top and the bottom of this table, or they could be recombinant classes. Those would be the things in the middle where we have a line that has a constitution where at locus A it's homozygous for the parent 1 allele, and at locus B it's homozygous for the parent 2 allele. Now, based on the genetic distance of this interval, we can model what the expected genetic value is of a QTL at any position inside that interval. And we're using some notation here that was introduced in an earlier lecture, but R in this table refers to the recombination frequency of the 2 marker loci, A and B. R sub A refers to the recombination frequency between marker locus A and the QTL at whatever position we choose to model it at. R sub B refers to the recombination frequency between the QTL position that we choose and marker B. So the question is, how do you know where the QTL is in this interval? Well, we don't, but we can model the QTL being either directly at the position of marker locus A or directly at marker locus B, and that would be the same as doing single locus mapping as we did in the previous slide. Or we could suggest that, well, let's say that the QTL is about 1 centimorgan inside the interval and it's closest to marker A. So then R sub A would equal 0.01 and R sub B would equal the difference between the interval overall recombination frequency and R sub A if the interval is small and we don't have to worry about interference or double crossovers. So given that, we can, given a QTL position in the interval, R sub A, R sub B just become functions of where that position is. The R itself is estimated from our MAT data. We consider it a known. It's actually estimated. And given all that, where the QTL is relative to these 2 markers, and given the marker genotypes at these flanking markers, we can figure out what the expected genetic value is of that genotype if the QTL is in there. And it's a function of A, which is the additive effect of the QTL, and it's also a function of those recombination frequencies between the QTL and the markers. And we demonstrated how this was derived in an earlier lecture. But what's nice about this is you have taken your set of 130 doubled haploids, and you can group them into 4 groups based on the marker genotypes. And given a QTL position in that interval, you can calculate what the coefficients on the additive genetic effect are. In other words, what the X values would be to plug into the regression model, and that will allow you to estimate the A effect, the additive effect of that QTL. So we fit that same regression model B0, which is the intercept, plus B1 times X plus E. The difference now is that the X that we are estimating is not necessarily directly at a QTL position. That X can be for any position within an interval between 2 markers. And here's an example. If we position the QTL directly at marker locus A in this example, and we assume that the recombination frequency between marker loci A and B is 10%, then the recombination frequency between A and the QTL is 0. R sub A is 0, and that means R sub B must be 0.1. And we can plug that into our table, and it turns out that the marker genotypes coefficients on the additive effect collapse into a very simple table. In this case, it only depends on what the marker genotype is at the A1 locus, because A and Q are completely linked. So if it's an A1 homozygote, we have a +1 X value, and if it's an A2, then we have a -1 x value. So we could fit that in the model, run the regression, get the estimate, and get the residual sums of squares from that model. Now we say, okay, maybe that's not right because we don't actually know where the QTL is, and we're going to move it just inside the interval. Let's move it so that the recombination frequency between marker A and the QTL is 2%. Then the recombination frequency between the QTL and marker B is 0.083%. Now we can plug that back into our table, and it turns out now that the marker locus A1 gives you a pretty good indication of whether or not you carry the QTL parent 1 allele or not. But if you have had a recombination, for those progeny where there's been a recombination and you have an A1, A1, B2, B2 genotype, it's more likely that the QTL is the Q1 state rather than carrying the parent 2 allele at the Q locus. So that x value turns out to be 0.6633, and it's positive. Whereas if you have a recombinant in the interval, and it's A2, A2, B1, B1 in that particular line, it's most likely that you're actually carrying the Q2 allele. But it's not certain. And that's why this value is not -1 in that case. It's minus 0.6633. It's really a probability that you're carrying the Q1, Q2 allele. It's not really a probability because this is not going from 0 to 1, but it depends on that probability. So what you can do is, and I've shown this in this table here, at the top I've suggested what happens as we move the position of the QTL through this interval. On the left side of the columns, we have it at the marker A locus position. At the rightmost column, we have it at the marker locus B position. And it can vary in there, and we move it at 2% recombination interval. So let's say we put it at 2% recombination inside the interval coming from marker A, and that would be the second column, and we just demonstrated what that gives us. And then we can move it 2% farther into the interval, so it's at 0.04 recombination frequency between A and Q, and therefore it's 0.065 between B and Q, and so on and so forth. And each time we move the position of where we're modeling the QTL, we change the coefficients for the additive genetic effect. And we rerun the regression, and we get new results, including a new regression coefficient estimate and a new residual sums of squares. And so we can calculate things like R² values and so forth for each position in the interval. Now, I haven't showed you all the output, but basically what you do is then if you say I'm going to scan through the entire genome at 1 centimorgan intervals, it's going to test every 1 centimorgan position. You could say I'm going to do it at 2 centimorgan intervals, and it will do it at 2 centimorgan intervals. And you can get an output where you can actually look at the results for every position it's tested. But what I'm showing here is just the peaks of the likelihood profile. And what that means is that the software can actually look through that big long output and just say where has the likelihood peaked in a particular region, and then presumably it goes down and then could peak at another position even on the same chromosome. So what I've shown are the first 3 likelihood peaks. All 3 are on chromosome 1. We have them at markers 34, 37, 39, and the positions are centimorgans 201, 215, and 257. And you can see for each of these we have a LOD score and then an additive effect estimate, which again shifts from positive to negative when you go down to that distal end of that chromosome. And we have these R² values of 5 to 7% more or less. That suggests that the QTL is associated with somewhere between 5 and 7% of the variation observed. Now, clearly again, the effect at near marker 39 at position 257 is negative, whereas the effect near position 215 is positive. So those are probably 2 different QTL effects. And now we can try composite interval mapping. And this is very much like interval mapping. The difference now being that before you do the interval mapping step, you first do a single marker analysis, one at a time, and you find the marker itself that explains as much of the variation as possible. In other words, the most significant marker QTL test. And you would fit that in your model. In this case, we would call that one X1, and that would be called a cofactor. And it has a regression coefficient associated with it. But we fit that in the model, And then we return and rescan the genome at each marker position, and we find the marker that has the second most significant effect after having fit that first marker, and we could add that one into the model. And you continue this as a multiple regression model building procedure until you come to some stopping point where you would say, okay, I have fit enough markers into this model to explain the data as best I can, and if I put another marker in there, I don't have good evidence that that last marker is going to fit. So there is some multiple regression model building that goes on. You fit in some number of cofactors, which I've noted here as going from B1 to Bn, and now we fit those in the model, and then we rescan the entire genome. So we go back and we get into the first interval, and we test positions at each 1 or 2 centimorgan positions inside the first interval, and we just, again, move our way through the genome, testing every position in the genome. So it's a combination of single marker factors controlling the genetic background and tests of specific interval positions. And then we look at how much evidence do we have for a particular interval position given that we've already fit these background markers in the model. And that's what a composite interval mapping output looks like. Again, these are just the peaks. You would have a full output that you don't necessarily want to look at, but it will show you that at each 1 or 2 or however many centimorgans you've chosen to step through the intervals with, each of those will be associated with a significance test and an estimate. So again, we find very much like what we found before, there is a QTL somewhere around position 215 centimorgans on chromosome 1, but now you see we actually have 2 QTL rather close together, 215, and then there's another one at 217, and each of those is given an additive effect estimate of 9 to 10, and the R-squared of almost 10%. And that's a positive effect, and then we look at the effect of the marker at position 2, sorry, that is not the marker, it's an interval position at 257.29, and you can see that the effect there is negative. And on, and we look through these likelihood peaks. My question for you is, do you believe this result? In other words, do you really believe that we have strong evidence for one QTL at position 215 centimorgans on chromosome 1, and a second QTL at position 217.9 centimorgans on chromosome 1, and they have very similar additive effects and very similar R-squares? And my suggestion to you is that's not probably correct, that in fact there's probably only a single QTL there. And what has happened is the likelihood curve has dipped a little bit between those two positions. There's probably a marker in between them, and the likelihood position may have dipped and then gone back up, and it has fit these things as 2 peaks. So don't just believe the QTL cartographer output when it gives you a set of likelihood peaks. You need to really look at them and think about what is realistic. If there were really 2 QTL that were 2.5 centimorgans apart, could we really separate their effects in a population size of 130? I don't think we can. So we need to be very careful about that. The other issue is that these effect estimates and these R-squareds values for these things, if you add up the composite interval mapping R-squareds for each QTL position, you could easily come up with a total R-squared that's greater than 100%, which doesn't make any sense. So these effect estimates and these R-squares are estimated in the context of that composite interval mapping model. So in other words, we are adjusting for the cofactors for the most part, but we're not adjusting for all the other QTL in the interval positions we've tested. There's one more hitch. As we're scanning through the genome, as you approach the position of a marker that's already fit in the model as a cofactor, if you kept that cofactor in the model, you would find no significance when you got very close to it, because the variation associated with that region has already been explained in the model. So what happens is the software will drop out any cofactors that are within a so-called window size of where you're testing the QTL. So you could say, let's choose a window size of 10 centimorgans. As I get within 10 centimorgans of a particular cofactor position, we'll drop that out of the model and scan without that particular cofactor in the model. And what that means is that these tests of additive effects and R-squareds really are not necessarily done with the same background model. And furthermore, it means that you can have these kind of funny results where you have two peaks that are quite close together, and it may have to do with where a cofactor is dropping in or coming in or out of the model. So the last thing we will do is multiple interval mapping. And the idea here is very similar to composite interval mapping, but instead of fitting the effects of a series of marker cofactors and then testing interval positions, we just go ahead and fit the effects of multiple interval positions simultaneously. So this is similar to CIM, except now we are fitting only the best interval positions, not these cofactors directly at the markers. It may turn out that the most likely position of a QTL is directly at a marker, but that would be coincidence. We don't force that to happen as we did in composite interval mapping in terms of selecting cofactors. Now again, though, we have this problem of we have a lot of markers. There are associations between the markers due to linkage and due to sampling issues. So it can be tricky to figure out what is the best possible model given a data set. There is some art to this. What is recommended at this point is to use the Bayesian information criterion to select the best model after using composite interval mapping to sort of identify the initial peaks to start with. This Bayesian information criterion is just a way of allowing you to judge whether or not you should add another QTL position into your model after you've already fit a certain number into it. And what it's trying to do is to prevent you from overfitting the model by just putting too many QTL into your model. There's no guarantee that you are actually going to select the best model with this. This is really an unsolved problem. There are too many possible models to test them all, so you do your best and hopefully you understand something about model selection procedures. So multiple interval mapping is nice because the end result of this is we get the simultaneous estimates of each QTL position reflecting the non-independence of QTL in each data set. And in our example here, after doing multiple interval mapping, on chromosome 1 you can see we've now fit two QTL. One is at position 215.9 and the other is at 257.3. And the effects are similar to what we were looking at before, but now we're not showing an output where we've identified two QTL peaks very close to each other near marker 36 or near position 215. So we've cleaned up that composite interval mapping result, and we have something that I think is a little more reliable, substantially more reliable, I should say. We also have these effect estimates that are simultaneously estimated, and we have these variances associated with each effect. And in this case, those things should not add up to more than 100%. And hopefully they don't add up to more than your entry mean heritability, because in this case we assume we should only be able to explain about 84% of the phenotypic variation of those means. So these estimates are preferred over the composite interval mapping estimates, and I think we can be more satisfied with this particular result. How do you know if you have overfit a QTL model? When one issue is, as I just mentioned, the total model R-square is near to or greater than the entry mean heritability. That suggests that you've probably got more markers in that model than really should be there. You sometimes see another diagnostic sign when you have closely linked markers that can be fit in the model, and their regression values, their slopes or their effect estimates, tend to be of large magnitude and opposite sign. The sum of these values may often be similar to the effect estimate of just one of the two markers fit without the second marker. And here's an example. Let's say you have two markers, 1 and 2, that are very close to each other. If you fit marker 1 alone, you get an effect estimate of 10. If you fit it simultaneously with marker 2, you get an effect estimate that kind of explodes up to near 30. And the effect of the second position, B sub 2, is minus 20 when they're fit simultaneously. It turns out if you look at the sum of those two effects, they'll be very close to B1 effect being fit alone. And what's happening there is there may be one or two recombinants in your data set that allow you to fit those two effects separately, but they're very, very poorly estimated. Very poorly estimated. And so you need to be very careful about that. You would need really very large sample sizes to fit the effects of closely linked QTL. So watch out for that.